Welcome everyone to another FPGA update here from our RISC-V based microprocessor homebrew DIY system stuff. What you just heard is nothing less than some original Sonic the Hedgehog melody from Sega Pico system fame here. Just looked for the, well, sort of kind of best VGM capture that I could find here, and to show you something more interesting than either Monkey Islands or SEC McCracken there from the other day. So this is vastly improved from the other day. If you're interested to the details, if you were only here for the Sonic the Hedgehog melody, then you certainly can rewind and listen to that a couple of times. Otherwise, also what you heard after the Sonic the Hedgehog was still our 16-bit, now just perfected, so everything working, mixing together, and I can present you here the details how this is implemented here. This, by the way, was a melody of VGM Rip's fame. But the topic of this video here, if you're interested in the details, if not, then just rewind and listen to that 1,000 times. Otherwise, the glory and amazing details here, also previous videos, there are 20 of those FPGA stuff. What is running here is, which, by the way, now that we captured it, I probably can or I can just unplug that here on those audio pins. So that is, of course, here the recurring IS-40 Icebreaker Lattice IS-40 FPGA that we are programming here, and with RISC-V core running that we just today overclocked a little bit, because why not? Unlike other channels, we also didn't drop it while doing that or rolled over with the office chair, allegedly occurring on other channels. Anyway, so as per the previous videos, in the Monkey Islands video I mentioned we had this running. So by the way, a short summary, what are we doing here? We are implementing some audio core. Previous videos a week ago, pulse width modulating, this here like direct stream digital, DSS, direct stream digital, DSD like super audio CD, basically pulse width modulating here with actually now in the meantime 13 megahertz, so high quality sort of anyway. And on top of this we have not only, so on our RISC-V core, right, so everything in one FPGA with the Pico RISC-V here and our audio stuff additional to that. And right now we have 3 square waves running, similar to PC Junior Tandy stuff, which is some SN76, something of that sort also something of that sort. Anyway, as used in the PC, IBM PC Junior and Tandy 1000, and also other systems like Sega Pico apparently. So what I have done in the Monkey Islands, I was already happy enough when some tone came out of there, because Verilog FPGA goodness was out, because we are we like to live on the dangerous edge here without even simulating this. Also coming soon to some, probably should be simulating this, but yeah, whatever, YOLO also works with just trial and error until it works there. So in the previous video, what I said, so the Monkey Islands and especially the SEC McCracken melody was still a little bit distorted and not perfect. And I immediately said, speculating, having implemented this, I immediately said, yeah, this mixing here is not ideal. We have here our 3 FM operators, and we were, for simplicity, only using unsigned integers, because, yeah, probably I should also mention, for those who are new to electrons and bits and stuff, of course in computers usually we represent numbers in terms of bits, 0 and 1s, and multiple of those usually grouped together in bytes, or higher quantities bytes being 8 bits, and those then represent numbers in power of 2's form from 0 to, in terms of 8 bits, from 0 to 255. And for simplicity I used just that, because that is what we for the most part here in Verilog on the FPGA are working with. And so what we need to do to make this easier, or easier for software and also for actually mixing the signals, is better not use this unsigned representation, which only has positive numbers, but actually implement 2's complement representation of numbers, so that we can also mix the signals better together, because we already here have not only our digital to analog converter, PCM pulse code modulated audio data coming here from the RISC-V CPU, but also additionally our in FPGA constantly running, right now 3, but later more, frequency modulated oscillating operators. And previously, why this sounded so well imperfect and some could say crappy in the first Monkey Islands and SecMac-Kraken version of yesterday, or when that was because we were not mixing the signals here perfectly together. We were simply, for proof of concept, adding this together in unsigned integers, which of course created a not ideal or not perfect waveform. I have here a small sketch, because basically we added, so the signal wasn't balanced around ground, but actually based upon the most negative level and just adding up. So so instead of like symmetrically around the ground plane, we were building signal up from the most negative level, and this certainly resulted in an imperfect and strangely distorted sounding signal. So today I set on here, except in the morning, if you have not watched this live stream, just little overclocked this from 12 to 13 megahertz. Theoretically, we could easily run at 16, just we don't have an PLL and other stuff right now free for it. But anyway, 7.5% or so faster, just for the fun of it. Previous video there. But after that, I set on here to actually implement this 2 complements logic. And of course, there are some good papers, which I will also link here below the article. So here's some from, what is it, even MIT, no less here, MIT educational stuff here. Arithmetic circuits and multipliers, certainly something you, if you're interested in this stuff, could probably read. And science, if you're new to this bits and electron stuff here and new to this channel, signed integers, which probably also I should usually explain more, probably sometimes I skip a little bit too much of the, for me, trivial details after 20 years dealing with, or more than 20 years. So back to the basics here, signed integers, instead of having just 0 to the all bits set, we have a representation that is naturally going from 0 if you subtract 1 in this kind of power of 2 representation of numbers. If you have zeros and you subtract 1, you would underflow this, not the opposite of overflowing, underflowing, so that a -1 would theoretically be all bits set. So going from 0, no bits set, all bits 0, -1, all bits set theoretically, and this tiny nifty little trick is what the computer we used for certainly nearly 100 years, probably soon or something of that sort. We used forever to implement negative numbers. There are also other ways. You could have just 1 bit as a sign that is, for example, used in floating point, among other things. But in this non-floating point whole integer numbers, this 2 complements logic is what usually is used. What is a benefit of this is that some operations like addition and subtraction works naturally. You just add and subtract numbers, and this works until you overflow, of course. So overflow meaning, of course, you can only represent a fixed range here from 0 to FF. And if you overflow this, then certainly this reps that certainly here what is commonly known as integer over or underflow. But if you stay in this valid range of numbers, then normal operations add and subtract work without further modifications. However, we need to take into account how this representation, when converting this to some output, because our output voltage, of course, only goes from 0 to FF. So if you, for example, read this paper here, like sign extending and other circuits for addition, that probably also shouldn't rap like this, If you implement this in Verilog, of course you could implement this yourself. Many things, as I said, addition and subtraction just work naturally until you overflow, obviously. But otherwise, there is, so if you implement this, is this even the right page? It's the right page. So there is some tiny little help for this in Verilog. You can declare registers and wires signed, and with $signed, you can also tell signed and unsigned here. You can also tell Verilog that you want this representation of bits and registers and wires used as signed and unsigned. So that is what I've done here. That was surprisingly error prone, especially if you do this the first time and don't run this in some simulator. So what I've done here now is declared here some of those registers signed, but it is not as easy. So just declaring something signed doesn't magically fix this. We had to tweak here quite some details. So I made the current digital to analog converter data signed. I also extended it by 2 bits because we are adding this frequency. We are adding the wave data, the PCM, the pulse code modulated wave data, together with the FM operators. So I wanted 2 bits of overflow headroom because converting this to the output, again, the audio signal sounds certainly completely distorted, kind of like an electric guitar or something of such an overdrive if you totally mess up the signals in terms of over and underflow. So instead of silently, like I think some MT32, probably first revision did of some overflowing bug, instead of silently over and underflowing and creating a totally like invalid signal, like certainly quite distorted signal, I wanted this clipping meaning saturating this to all bits or 0 bits set. This is why now we have here 2 bits of overflow headroom. And starting with the FM operators, where are they even? Somewhere of audio here, here. So I also made the FM operators output signed. So these are the FM operators registers to be used, and the output wire here, now it's signed. Again, previously it was unsigned, now it is signed. However, we also need to take this into account when generating the signal. Previously we generated just 0 and full scale for the FM operators because previously it was unsigned. Now we are generating if it is running. So also now we take into account if it's running. If it's not running, then we output 0, and only if it's running, then we output the volume. If the state is set for the square wave, we output the volume or we output the negative volume. So just what you would expect of oscillating there around your ground plane. So this is a change in the FM operator. So far so easy. And then additionally, we need to mix this here together. This is also not much changed, except we have here now, you might spot here that is now using 3 greater signs. This is because this is now some arithmetic shift right. Previously we also already shifted this right. Now 3 greater signs in Verilog are arithmetic shift right, meaning a normal shift would, if you shift this out, a normal shift would, the bits, the vacant bits that are now becoming empty would become 0. So this is arithmetic shift right. The only difference is actually taking the sign into account. The sign, positive or negative, is accidentally the last bit. So it's actually simply replicating the first bit, the most significant bit. So if it's 0, it remains 0. If it is 1, then the 1 is the fill of shift is actually all replicated and filled with the sign bit. So this is obviously before, otherwise we would convert negative numbers. So if you, for example, -1, here all bits set, here of -1, if we otherwise shift this without an arithmetic shift, we would 0 the first most significant bit, and instead of becoming 0, or actually it would still become shifting, so actually -1 would remain -1, right? But instead of remaining -1 for shifting this of all bits set to the right, we would make this the highest positive number, and basically accidentally wrap this around, like it's not like really even overflowing. Well, it's kind of sort of like overflowing of strangely messing up -1 to plus full scale. Certainly sounds again totally distorted. So that is only the top level stuff. So this stuff was relatively quickly, like 20-30 minutes you have this done. The most complicated part was this one. This took me actually way longer than that. This few lines of code to get right. It turns out each time you are both of those sides here of a comparison in Verilog are, if one of those is unsigned, this is comparing or treated as an unsigned. And if you want to have a signed comparison, both sides need to be signed, and it's a little bit tricky, especially if you do it the first time, although you have this helper here similar to C. But of course, again, the implementation is different and the devil is in the detail. So getting all of those took me quite a while, especially doing it the first time. The next time I implement something like this, it certainly will be much easier. So what this is doing is this is clipping this. So we are adding all of those signals together. And of course, we do not want to lose precision of our 16-bit precious pulse code modulated PCM data. So we add this together so this can overflow, right? So we can have, oops, I also pressed the button. I think at least did I? This pulse code modulated signal can be full scale. So this can be from plus 7 FFF to like minus 8,000 or so to say hex. And if we add this FM operators, although we arithmetically shift them a little bit not to overflow here in the FM modulation, but together with the PCM signal, this will overflow if you have both running. So to prevent this overflow here in the analog audio, I'm saturating this, meaning this is why we have 2 bits headroom. Also why I already included a little bit of more headroom, because soon I want to have here more than 3 operators running and more than a square waveform. And saturating or clipping, meaning that instead of wrapping this from full scale hex 7 FFF, again full scale like 1 volt or something line level, whatever you have on your analog output, to the minus range, again totally distorting the signal. And you hear this. So like for an hour I was drafting this stuff. By the way, I think probably you don't even need else clauses. I probably another day need to check what uses is generating here precisely. I think you don't need else here. You can probably write this first, and then if greater, I think with this non-blocking statements, I think probably the last effective, like non in some conditional, takes effect, but correct me if I'm wrong, I need to check this another day. Also initially I had this here in one assignment, like if overflow, otherwise this, if positive saturations and this, if negative saturations and this. However, this was a little bit hard to debug. I need to check later what is the most efficient in terms of saving some logic elements here. So, but after long trial and error and debugging this, just with listening again, if this is wrong, you will hear this instantly that the signal is totally distorted. So again, this is sign data, comparing this here. Again, with a sign left out, it's comparing unsigned, and then you get all kind of clipping effects of trimming half of your signal wave away and causing total distortion. So this is if overflowing in the positive range, outputs so why is this? So this is actually from 0 to full scale, right? So this is our pulse width modulation on the FPGA output pin. This is why we are converting from negative to positive signed full scale to the pulse width modulating from 0 to, so from 0 ground to plus 3.3 volt. And this is why this is outputting here from 0 to full scale, all bits set on the analog digital analog output pin. So again, positive overflow over 7 FFF, then full scale, negative overflow below minus full scale of minus 8000 hex, then 0, and if in between, then properly converts this here. This was also a little bit tricky in terms of making sure, because this addition otherwise is resulting in a 17-bit with carry overflow, and because our pulse width modulating previous video, if you want to see that details, is 17 bits, this was causing our direct stream digital output pin to overflow more often than it should for this pulse width modulated dithering. Again, details for that previous video. So this again, surprisingly tricky, probably costed me 45 minutes to get the 3 lines correct of code, but also recurring theme here. Why is software and hardware development a little bit expensive? Because yeah, even you can spend 45 minutes, especially when you do it the first time after a decade, then getting all these details right. Also certainly best either in a simulation or something of that sort. And yeah, so this is our system bus, nothing changed here. However, because we now changed the representation of the PCM data, I had to freshly convert this because previously on our RISC-V site here that we are obviously still running here, let me show you. So previously I actually converted this for inclusion in the firmware. Again, we are running here bare metal, low level, without any operating system or such safeguards on the RISC-V here, and some firmware written in C. So let's see hex dump. For this, I converted this with SoCs. Here stay golden from not to trigger again. Last time we triggered some copyright claims here on YouTube. So some YouTube free audio library stuff. Previously I used here SoCs, this generic Swiss Army knife of audio conversion stuff of open source in your favorite Linux distribution. Bits 16, big endianness, encoding. So previously we used unsigned integer. Thankfully, SoCs supports all of those details. We downsample this to mono 1 channel because that's what we are having right now. And then let's see SoCs, whatever. Yeah, so to UART raw. So to show you how this looks like, now we converted this to an unsigned integer, what we were using before. Let's hex dump this here, canonical representation of UART raw. And this is how this looks. And so let's just double check here. So unsigned integer, and this is exactly what we were expecting in terms of the music starts with a 0 level of silence. So this starts at 8000 hex because again this is unsigned, right? And then it starts after a little bit of silence. It starts to have a little bit signal, like thankfully for this example, amazing example, just 1 up, so 1 to the positive side. A little bit noise there, 1 to the negative side. So this is a little bit, one bit noise in the beginning of this song, around 8,000 hex of unsigned integer. So the new code, and again, then with this SoCs, I directly embedded this in the firmware for you to hear. With signed, so I had to change the firmware embedded data because now it is signed. How it usually is. Again, you see it's just a representation of how you interpret this bits and numbers. And then now this is signed how you would more normally, like more naturally, around a 0 ground level. And when we take a look at this hex dump of signed data, you see correctly that this is now, instead of dithering 1-bit noise around 8000 hex, we are now here starting with a more natural level of 0, and then +1. You see it's not even audible, there's 1 bit of noise, not like your record players of vinyl fame. This is true digital 0, non-noisy signal stuff here. And then -1, just as I said, to complement logic of 0, -1 is all bits set here. And so this is converted. You see then after a little bit of noise in the beginning, we start to get eventually a little bit more signal, and then you see here the signal after fractions of a second starts to eventually, eventually. So yeah, eventually this starts. So this is how audio data looks in the digital domain after initial silence and 1-bit noise, eventually some more signal amplitude changing. So of course I had to include the new firmware here in the new PCM coded signed data, and aside from this, nothing changed, except like now our FM operators sound amazing because they no longer add up from a 0 level. Strangely, they're in virtually negative number space there, and instead correctly add, like you would mathematically add up signals here around a 0 level, and that is the difference between sounding like, yeah, proof of concept, you can recognize the Monkey Island melody, and nowadays, here after 1 day later, which by the way we can now play once more for all the new people who tuned in. Let's unmute this and connect again to the, either with this or with screen R. Yeah, and as you hear, we have right now both of those running, PCM coded wave data as well as FM operators. So on a quality much higher than the original, because the original PC Junior certainly didn't have 16-bit direct stream digital coded PCM data wave playback. And on the hardware Verilog level, again, this is a system bus here. And for those who are new to this project, we have here the DEC data, again, not yet implemented. Soon we have stereo, because certainly stereo as it's 2020. And here our 3 operators. Also, by the way, fun fact, soon we will have next to be implemented. Also, I can already add this comment of to make this totally feature parity and soon way better than the original. Also the noise channel, that then all the VGMs, then you would have a hardware RISC-V based hardware player for VGM music of that sort. So that would be a noise channel, would then be 8, 9, that would be 8, so 9, A, B, I think C, and not yet implemented noise channel, and later then also other waveforms, right now square like the original, but soon, I said this before already, to have even more amazing sound. Soon triangle, sawtooth, and maybe if we are super lucky, some kind of sine approximation. Not really sure if we will have enough logic elements free for that. But yeah, welcome everyone. Let's see, we have quite some comments as usual in the audience. Let's see what I missed while going through this. And even if you watch this later and have some comments, tips and tricks, also yeah, I muted this, leave it in the comments below. Always trying to read them, and anyway, answer questions also later in the on-demand video archive stuff. Let me just resize this browser. So that is it on this progress. So making quite nice progress. Sound relatively feature complete, except some right channel and more waveforms. Otherwise keyboard mouse. Otherwise homebrew microprocessor channel. If you want to implement some game, feel free to draft this already in terms of Pac-Man, Sonic, you name it. Let's see. So yeah, questions were, was it Sonic? Yeah, that was Sonic. So let's see. Christian, it's bad that can't already hear tune and sound effects in what? Is it bad that he can already hear and tune sound effects in his head, seeing the title, playing those games too much? And yeah, that is certainly good. That is a good thing, not a bad thing. Probably so. Mr. Wong writes, Mega Drive Genesis Sonic games, pretty sophisticated collision detection system, pseudo pixel collision detection. That sounds amazing. Terminal-based collision detection. Terminal? It was supposed something height map. So Big Endian, people like Big Endian, well, in my opinion, Big Endian is easier to read anyway, because Big Endian representation is as seen on in source code. In my opinion, Little Endian is always Little Endian on the bit level there in the hardware. In my opinion, not as easy because it's always reversed. I don't quite understand, because you see here, this is exactly how you would write it with Big Endian, natural notation there of numbers. This is why, in my opinion, Big Endian mostly more natural, which certainly explains also why it's used for network endianness. Welcome, Electron Ash there. And what else do we have going on? So unsigned value always positive, just do wire signed my signal something. So to convert an unsigned value always positive, unsigned was declared as 708 something, whatever. So complications in our case were because we had some overflow and conversion. So again, the biggest challenge here, except changing the FM operator stuff to correctly negative, and which, by the way, this is also slightly, you need to be careful not to program this to use in too high value. This is why anyway, but programmer needs to be careful. The biggest stuff was here the saturation here. That here was the most tricky part. We could certainly theoretically try to do a scrollback of, I compiled actually LLVM, so I have LLVM scrollback, but theoretically we could test if my suspicion is correct that you can write it like this. By the way, if you are an Verilog master, then you could let us know what is the most efficient way to write this. I think that probably should work. Do I have, we can probably just flash this like this. Takes 50 seconds to synthesize. So here, PicoSoc and PicoSoc. So that takes 50 seconds or so to synthesize on an AMD Ryzen 3950X, because it's mostly single core. Anyway, do we have here Big Endian? So Electron Ash also prefers apparently Big Endian, I guess. Anyway, correct me if I'm wrong. Welcome Glauco, thanks for asking how we are. We are doing fine. I hope you all are doing fine as well. Mr. Bong says Little Endian is easier to implement on a CPU. I would say it's mostly transparent. The only thing is, also RISC-V unfortunately is Little Endian by default, although they write in the specification you could implement RISC-V with Big Endian. The only reason I found in the specification, also previous video discussing RISC-V instruction set architecture some 6 months ago or so, the only major reason they write in the specification is Little Endian for the compressed instruction set, because that is the only complication probably with Mr. Bong's CISC, CISC CPU, that if you have a variable length, then like the CISC x86 of Intel, then the challenge is where to start. So for Intel it makes sense in as much as Intel x86 does not make sense. Did we already synthesize? That was fast. How long did this? Anyway, this is why variable length instruction set, you start reading from the address and then variable length certainly. Then Little Endian makes more sense in the way it doesn't make much sense. But for RISC processors using a fixed word length, anyway, it probably should be mostly completely transparent whether it is Little or Big Endian. The left or right to left order of the logic elements and transistors certainly don't matter there in terms of, it's not like they are falling out left to the right, or when you turn them upside down, the precious electrons. Anyway, so let's see. It could be headphone wearing people. They are warning it could sound awful if this Verilog synthesizes to something entirely different, then it could sound completely distorted. So headset warning, but maybe it works. Let's see. that certainly sounds correct. So that is what I expected. I could theoretically another later, but already a little bit too much time for all these fun projects here. So theoretically, we could investigate what of those ways of write this. So you could write this with if then else. Not really sure. We should probably, how many logic elements did we use up for that anyway? Also scroll back. So we are already using 90% of the logic elements, and this is only because I disabled compressed instruction set because I was running out of logic elements here. So we are right now using 94. This is actually slightly more. So I wonder, maybe this is actually worse. That is interesting. So we are using 5002. I think it was less before. So let's see if else, and let's see to how many we are synthesizing now. Also very theoretically. So you know what? We have quite some people watching. We can also fully try this here. Let's synthesize this again. That's what we have an AMD processor for. So here 10 0-drop frames. It is also thank you to Vodafone here. Today I have 0-drop frames. It's not always we have 0-drop frames. The Electron Ash asked, what is the music just afterwards? That is some golden. You saw this some 10 minutes before when we converting this. As I said the first time I used Tori Amos, which even in the crappy quality got copyright content strike matched by Google. And people immediately said, why do I not use this? Hey, we are using a little bit less logic elements, so 4000. So there you have it. Explicitly coding this if then else. Using a couple of less logic elements here, we saved us a whopping, was it 5000? What did we have? 5002 or so? Let me scroll. So we probably saved 10 logic elements. Let's scroll up. What was it? 5000 and 5002. So we saved a whopping 10 logic elements. That is certainly amazing, as we have only 5000 and a couple of more. So yeah, that probably I wonder. Did I, by the way, trumpet sound? Yeah, sorry, I probably. So the track name is Golden, so that is YouTube free audio library. This was Golden. We can check in a second here so this is flashing here of that frame. Anyway, YouTube free audio library Golden, something stay golden, something golden, MP3 or whatever. I wonder slightly if it is even more efficient now that we have this working. Initially, before this was working and I was still drafting this, I was coding it like that. So that would be if this comparison, if greater this, then that. Else, if less than that, this. And otherwise, just this. Let's see if this also works and how many logic elements that uses. Let's see, this was SOX, so the title, yeah, Stay Golden, some free YouTube library stuff of not getting copyright content striked here again from those. Let's see, need to start using RISC-V soon, especially logic handling something SD codexes. Cool stuff. So let's synthesize this again and see if it still works. Also, we made a typo. We now have in line 191 deck data. Here also with modulation. So always watch. By the way, I should disable some Verilog files. Disable implicit declaration. I would prefer that this errors out instantly, because otherwise these errors are often a little bit quick to scroll out here out of the terminal. So by the way, how long did the synthesize? It prints the synthesis time. This design, actually, wait a second. Yeah, so this design would be good for 16 megahertz on this IS-40. I wish we would have some PLL-free for something of that sort. This is funny. This is using more logic elements. That is crazy. This is unexpected. So you really need to be careful. So this, you would think this is the most efficient way to code this, but apparently not here. We could actually finished synthesis, so this is using way more logic elements totally unexpectedly, although maybe you're a Verilog wizard or guru, then certainly you probably know why. But yeah, this is unexpected. And this also explains why I had to disable the compressed instruction set support from the RISC-V core, because I was constantly previously running out of logic elements already, and that certainly is not fun if you design something and you constantly, it doesn't synthesize 102% of your logic elements used there. So yeah, I'm curious if that works okay, but after that we can already start to revert this, because this certainly makes no sense to make it less readable and use more logic elements. That is, maybe we should tell the uses, authors and masters there, maybe they want to optimize this. I would think this probably should maybe have the tendency to optimize to the same optimal design, but maybe not so. If positive saturation, then this. If negative saturation, then this. Otherwise that. Let's screen. So I think it should work, but sometimes you have a surprise. Yeah, it sure works. Fun stuff. So yeah, all three combinations work, and the one that I thought would be the most efficient uses the most logic elements. So we all learned something, hopefully, at least even I did. Always the best to, oops, what was it? Pick some list. I think I hope I didn't destroy that. Doesn't, whatever. So let's resynthesize this again. And you see, while you can certainly use an aging Intel Core i7 or something, you certainly, even for this kind, well, it's of course already a larger design with the whole, you're using 5,000 logic elements here on this FPGA with Pico RISC-V, Pico SoC in terms of simple UART, our video core running here with text attribute VGA palette kind of stuff, plus flash interface, audio interface, and yeah. So we are using, yeah, this is by far the smallest design. The other version uses 10 logic elements more, and the other version, what was it even? Was it 40 or 50 more? That was really crazy many more for, in terms of, how many was it to quote the correct number? Yeah, 43. So yeah, this is, in total, it's using 51 logic elements more. That is certainly a quite whopping number, so be careful what you're writing then. Verilog. With all this design, certainly, if you want to squeeze the most out of it, you can always review here details. I said this before, especially in the VGA core, we have some palette and pixel registers that are way larger than we need. For example, we have 24-bit for color, although we have only 4-bit color output per channel, 12-bit color output, so we could theoretically, the VGA core, optimize quite some by cutting all the color components in half and stuff. But yeah, that is certainly something for final, when we finally run out of the last logic elements for keyboard and mouse, then maybe we need to do some last minute optimizations there. And let's get a Spartan 6, and those are supported by users. Yes, although right now this is still enough. Maybe later we could do this, but right now Aston sends this over, so we have fun using that, but later indeed we could update that to whatever. What do we have? There's some video, so trumpet sound, RISC-V, especially something, implement line wrapping in some editor. What an EROM, so copy link address, what did. So anyway, that's mostly it for this video. Quite some progress, so like kind of sort of, oops, something went wrong, whatever, something, what? Studio, watch, no, whatever, I check later. I hope you learned something, even if you're not into FPGA stuff and want to do regular low-level programming. Maybe if you're new to all this electrons and bits and pieces, then to complement logic and other fun stuff might be something for you. Let's take here, so this is of course, by the way, did VSV git diff. I think this is already committed. Yeah, this is only what, right, the noise channel. So here, this for sure works. Thanks for watching. I hope you learned something. If you have comments, leave them there down below. Otherwise, hope to see you soon for the next videos and live streams. And otherwise, I hope you enjoy all this FPGA and audio project.